Another way to solve a blank differential equation. Non-homogeneous, linear. Yeah, I was looking for linear, but I'll take non-homogeneous. Yeah. No, because it doesn't work for any first order differential equation, only if it's linear. The method of true or false? The method of integrating factors requires guessing mu of t. False. This method does not require guessing, and that's in contrast to the method we learned last class, which was the 3-step process, and step 2 involved the guessing step. So which do you prefer, the 3-step process or the integrating factors? There's no wrong answer here. Whatever you wrote is fine. You could have said A or B. You could have said it depends. You could have said I don't know yet because I don't get integrating factors. Whatever. All right, so we're going to start class by sort of developing what the heck and like where integrating factors comes from, why it works. Then once you sort of see where it comes from, it's very rote. You can just apply it and it just works. Okay, but before that, I'm going to show you where it comes from. Okay, so dy dt equals a of t y plus b of t. This is a linear, non-homogeneous differential equation. All right, so I'm going to do a side here. All right, so remember that if I want to take d dt of y times mu, and both of those things are functions of t. That's y of t times mu of t. How do I do that? The product rule. Yeah, so this would be mu times dy dt plus d mu dt. I should have given myself more room to write this. Okay, so that's mu times dy dt plus d mu dt times y. Okay, so that's just the product rule. Yeah, we're just using full derivatives, no partials today. The only time we've ever seen partials is in the existence and uniqueness theorem. I think that that's the only time we'll ever see partials. No guarantees, but I'm pretty sure. Okay, so let's just keep this in the back of our minds, right? That this is the product rule for a function y and some function mu. And what we're looking for is the function y that solves this differential equation. So first thing I'm going to do is I'm going to rewrite this as dy dt minus a of t y equals b of t. So this is also something we did when we were solving with the 3-step process. It helped us guess by putting everything with y's on one side. However, I'm just going to do a quick rewrite here, and I'm just going to say, just for the sake of simplicity, let g of t be negative a of t, so that we don't have any negative signs in the differential equation. So this is, my differential equation is going to become dy dt equals, plus g of ty equals b of t. Okay, so nothing crazy yet, just some small manipulations to the differential equation. All right, now, this whole mu thing. So there's some mu over here that if I took the derivative of y times mu, I would do the product rule and I'd get this. So if I have some function mu, it's hard to know what it is, but just imagine that we had some function mu, and you're going to multiply both sides of your differential equation by mu of t. So on the left, I'm going to have mu times dy dt plus mu times g times y right? I'm just multiplying this term g of ty by mu. And I left off the of t's part just to make things look cleaner, equals b times mu. So I multiplied every term on both sides of the differential equation by mu. And mu is some function. Okay. Now, compare the left side of the differential equation to the product rule that we wrote over here. Are they close? The first term is the same. We've got mu times dy dt and mu times dy dt. And then here I have mu times g times y. And over here I have d mu dt times y. So the only thing that differs, right, is that this mu times g has replaced this d mu dt. So if those two things were equal, if we chose mu so that d mu dt equals mu times g. So this is my aside here, right? Choose mu such that d mu dt equals mu times g. And g is a known thing, right? It's from the differential equation. So this d mu dt equals mu times g is another differential equation. Can you solve that thing? Remember, g is a function of t, and so is mu. Yeah, you can. So you can solve it by separation of variables. So I would have 1 over mu d mu equals g of t dt, right? And then you can integrate both sides. So the ln of mu is equal to whatever the integral of g of t dt is. In an actual example, you could do this because g of t would just be some function of t. And then mu, raise e to both sides, so mu is going to be e to the integral of g of t dt. Right, so we can choose mu in a special way so that the left side of our differential equation looks like the product rule. Use what? Oh, yeah. Yes. Yeah. So, yeah, we haven't actually taken an integral yet. You're right. Yeah. All right. So once we've done that, once we've chosen mu so that mu times g is actually equal to d mu dt, rewrite this, and I have mu times dy dt plus d mu dt times y equals b times mu. Okay, so I replaced mu times g with d mu dt because I've decided I'm going to choose mu in such a way that those two things are equal. Okay, that's what all the aside is on the right. But, yep, they're full derivatives, no partials. Yeah. Okay, so now this left-hand side of my equation, because it's the right-hand side of the product rule, I could say that is actually the derivative of mu times y. Right? This looks exactly like the product rule. So if you go back over here, I have this thing, so I could replace it with d dt of mu times y, or y times mu. All right, and then the last step is to integrate both sides. So integrate, and what is the integral of the derivative of something? Just something, yeah. So my something is mu times y, and that's just going to equal the integral of b of t times mu of t dt. And then finally, I ran out of room. To find a y, right, to get y by itself, just divide both sides by the function mu. So the last thing is that y is 1 over mu of t times the integral of b of t mu of t dt. That is the formula, right? That's how we would get the answer. But in practice, we don't. I'm not actually going to use that formula. You can if you want, but that's where it comes from. That's the integrating factors of mu times y. So from the previous step, this thing is exactly the product rule. This is like first times the derivative of the second plus the second times the derivative of the first. So I'm working backwards from the product rule. And I said, so that thing is exactly the derivative of mu times y. So for a summary, to find an explicit solution to a linear differential equation, if it looks like this, right, if it's linear, first write it in this form so that it looks like dy dt plus g of ty equals b of t. First, you compute the integrating factor. Mu of t is e to the integral of g of t dt. That's this thing, right? This is called the integrating factor. The word factor is in the name of that thing because you are now going to multiply both sides of the equation by it. Okay. And integral is in there because there's an integral in it. So note that you only need one integrating factor. So somebody asked me about the plus c, right? So when you're calculating the integral of g of t dt, just take the most convenient choice for the arbitrary constant c. You don't need every possible integrating factor. Any integrating factor will work. So typically, if you have a plus c, just use 0. If it's like a coefficient, use a 1. And then you determine the solutions of the differential equation by multiplying both sides of the equation by mu of t and integrating. All right, so let's do an example. So we want to find a general solution to the differential equation by an integrating factor. Then we're supposed to check by using undetermined coefficients, which is the process we learned last class. I won't do that. Okay, so first, I need an integrating factor. So mu of t is always e to the integral of g of t dt. So this is e to the integral. G of t in this case is what? It's just 3. It's just the thing on the y, right? It's just 3. So this is e to the integral of 3 dt, which is, what's the integral of 3 dt? 3t. So this is e to the 3t. And I only need one integrating factor, so I'm not going to write plus c. I'm just going to take that c to be 0. So this is my integrating factor mu of t, e to the 3t. Okay, so my next step is to multiply both sides of the differential equation by the mu of t I just found. So I've got dy dt plus 3y equals t. Multiply both sides by e to the 3t. All right, so when I distribute this e to the 3t, I have e to the 3t times dy dt plus 3y e to the 3t equals t e to the 3t. Okay, this is the result of a product rule. This is the result of taking the derivative of a product. What product is it? The derivative of what product? e to the 3t, and y. Yeah. So e to the 3t would be the first function. So this is first times the derivative of the second, plus the second, which is the y, times the derivative of the first. And the derivative of e to the 3t is 3e to the 3t. So this is the product rule performed on y times e to the 3t. So my next step is that this is actually d dt of y times e to the 3t equals te to the 3t. And then you integrate both sides. Integrate, integrate. Yes, with the integrating factors, you're always going to end up with something that looks like the product rule and you're going backwards. Yeah. So the whole purpose there is that now it's easy to integrate, right? Because the integral of a derivative is just the thing, right? So the next step here is just y times e to the 3t. And then I have to do the integral of t e to the 3t, and I think I need another page. Hold on. Okay, so the integral of the derivative is just the function itself, and that equals the integral of t e to the 3t dt. Okay. Anybody know how to take the integral of t e to the 3t dt? Yeah, by parts. Yeah. So let's, I'll do it as a little aside over here, or a long aside maybe. So what is, what do you have u and dv be? Remember by parts? It says that the integral of u dv is equal to u times v minus the integral of v du. Yeah, so I need to choose u and dv. So what did you want to let, I'm sorry, Todd, I couldn't. Yeah, if we let u be t, that's going to help us out because when you take the derivative, it just becomes 1 and things will actually get simpler. So that means that du equals dt, right? And so that means that leaves dv would have to be e to the 3t dt. And that means that v would be the integral of that, which would be 1/3 e to the 3t. And then we plug into the formula for by parts. So u times v would be t times 1/3 e to the 3t minus the integral of v du. So that's minus the integral of 1/3 e to the 3t dt. All right, what's the antiderivative of 1/3 e to the 3t? 1/9 e to the 3t. Plus c. All right, so we now have this integral. Come back over here and I have y times e to the 3t is now equal to the antiderivative of that thing, which I just calculated is t over 3 e to the 3t minus 1/9 e to the 3t plus c. And then the very last thing I have to do is solve for y, right? Because that is the solution to a differential equation, a function y of t. So I'm going to solve for y in terms of t, and I just divide by e to the 3t. So these cancel, and I have y equals, those are going to cancel, so I'm going to have just a plain old t over 3. Those e to the 3t's are going to cancel, so I have minus a ninth. And then I have plus c over e to the 3t. Sure. Oh, you can't, e to the 3t is not a constant. So c over that thing isn't a new constant, it actually varies. So you can't. If that were like c over 5, you could smush them into a new constant. Or c over plain old e, you could smush them into a new constant. But because there's a t in there that's making that vary, this term is not constant. It varies. All right, so I mean, it's kind of a long process. Sometimes there's a lot of manipulation that you have to do. However, it always gets to the answer without having to do that guessing step. Okay, so there's the pro there. And the key is recognizing the product rule backwards, right? All right, so, oh, I'm not done. Okay, sorry. In the class activities, I'm going to have you solve. Oh, yeah, no, sorry, I got to go back. I forgot that was there. Okay. All right, so we have another more complicated mixture problem. So we did one like on one of the first classes. This is another one. We've got a pond. It has an initial volume of 10,000 cubic meters. Suppose that at time 0, the water in the pond is clean, and the pond has 2 streams flowing into it, stream A and stream B, 1 stream flowing out, stream C, and the picture didn't come through. All right, there we go. So here's our picture. We have 2 streams that flow into the lake and 1 stream that flows out. Okay. There's 10,000 cubic meters in the lake at the beginning. All right. So suppose 500 cubic meters per day of water are flowing into the pond from stream A. So 500 cubic meters per day of water, right? And then 750 flow in through stream B. And 1250 flow out through stream B. Right, so the same amount is going in as is going out. All right. At time t equals 0, water flowing into the pond from stream A is becoming contaminated with road salt at a concentration of 5 kilograms per 1,000 cubic meters. Okay, so we've got a concentration there. And then the water in the pond is going to be well mixed so that the concentration is constant. That may or may not be a good assumption. And to make matters worse, we're also going to assume that at time t equals 0, someone begins dumping trash into the pond at a rate of 50 cubic meters per day, and the trash settles to the bottom of the pond. So it's actually going to reduce the volume of the pond, of how much water it can hold, because there's stuff taking up that room. And to adjust for the incoming trash, the rate that water flows out is going to increase to 1,300. So we're losing 50 cubic meters a day to trash. So that means that an extra 50 from 1,250 to 1,300, an extra 50 has to flow out every day to account for that trash. So, so the banks of the pond do not overflow. All right, so we want to write a model for S of t, the amount of salt in kilograms in the pond at time t. All right, so the change in the amount of salt with respect to time is ds dt. And that's going to be the rate salt enters minus the rate salt leaves. All right, so I'll do over on the side here, we have to calculate what those two things are. It's not given to you directly, but we do have enough to figure it out. Okay, so rate salt enters. So the concentration is, well, the water is entering in cubic meters per day, 500 cubic meters per day. And then the concentration of the salt is 5 kilograms per 1,000 cubic meters. 5 kilograms times 1,000 cubic meters. So you see the cubic meters are going to cancel, and we're going to get kilograms per day, which is the rate at which salt is coming into the pond. Cubic meters cancel, and I get 1,000 kilograms. Sorry, 2.5 kilograms per day. So over in my differential equation, I put in a 2.5. All right, then I have to figure out the rate salt leaves. So again, same thing we did before, it's concentration times water speed. So the water speed, we know that's 1,300 cubic meters per day. Water is leaving. And then I have to figure out the concentration of salt in that water, right? So how many kilograms per cubic meter there are, so that my cubic meters will cancel. So how many total kilograms of salt are in the pond? At any given moment? Say it out loud. S. Yeah, we don't know. That's what we're trying to find, right? S of T is the amount of salt in the pond, right? So S is the amount of salt in the pond. So that's what goes on top here, S. No, because the 50 kilograms per day of trash, like that stays, that's always 50 kilograms per day. So no, because they're both per day, right? So no, trash is settling to the bottom of the pond.
Right, so eventually it will fill up. Or is it just the water?
Yeah, eventually the trash will fill up and the pond will empty. Yeah.
So it would be increasing each day. Right?
No, the rate is always going to be 1,300 until it empties, right? It's a constant rate out until it's gone. I do. All right, so the amount of salt in the pond is S, and how many cubic meters are in the pond? 10,000. But is it constant, the volume of the pond? No, 10,000 minus 50T, right? The pond volume is decreasing by 50 cubic meters each day. So simplify this and you get 26S. 26S over 200 minus T. Cubic meters cancels. All right, so that is my rate out, 26S over 200 minus T. Yep. Because there was no salt in the pond at time 0. S of 0 equals 0. So this is an initial value problem, which means there is one particular solution. There is one function that can satisfy both the differential equation and the initial value. So I'm going to try to sketch it on a slope field, right? I'll have you solve it using an integrating factor in the activities. But for now, let's just glance at the slope field. And my initial value is that at time 0, right, this is time, this is salt in a pond. So at time 0, there's 0 salt. So there's my initial value. And then I'm going to try to follow the slope field, and it looks like it goes up very quickly and then heads down like this, something like that. Does this solution make sense? Does it make sense that the amount of salt in the pond increases very quickly and then decreases to 0? Yeah, how come? There's no water left. Yeah, everything has flowed out. Yeah. So it's going to increase quickly because we have salt is flowing into the pond and water is flowing in faster than it's flowing out. So the salinity is going to go up and up and up and up until the pond starts to empty.
But it would
Right.
never go to 0. Because even though water is, the total water is water entering the stream is still.
Yeah, but it's feeding in slower than it's draining.
Right. But like there would still be a constant.
Well, no, because actually there's no place to put the water because it filled up with trash. So it would just flow over it. Yeah. So there'd be no salt in the pond. Yeah. No pond. Yeah. Yeah. Okay. Now you can start the activities.